Today, we are diving into the biggest story of them all, the origin of our universe. But this isn't just a story about physics. Nope, it's a story of a fierce scientific debate, a real cosmic rivalry that completely shaped our understanding of, well, everything.
I mean, it's the most basic question you can ask, right? And for most of human history, the answer seemed kind of obvious, almost intuitive. But as we're about to find out, our intuitions about the cosmos was spectacularly wrong.
You see, the idea of a static, unchanging universe, one that's always been here and always will be, that was the standard view for centuries. It just felt right. But then, in the early 20th century, a bunch of mind-bending ideas and some truly shocking discoveries started to just tear that old picture to shreds.
So, the first big clue that our old model was toast came from a pretty startling realization. The universe wasn't just sitting there. The cosmos itself was moving, expanding, and that changed everything.
And what's wild is that the seeds for this new idea were sown in math long before anyone saw it in a telescope. Even Albert Einstein himself, his own theory of general relativity was practically screaming that the universe was dynamic, but he just couldn't accept it. Philosophically, a static universe just seemed neater. He even fudged his own equations, adding what he later called his biggest blunder, a cosmological constant just to hold the universe still. But other folks, like Friedman and Lemaitre, they just followed the math where it led, proposing a universe that could expand from a single point, what Lemaitre called a primeval atom.
And then came the proof. In 1929, an astronomer named Edwin Hubble made a discovery that would change history. He saw that the farther away a galaxy is, the faster it's moving away from us. Think about it like dots on a balloon that you're blowing up. From any single dot, it looks like all the other dots are rushing away. The universe was, without a doubt, expanding.
Okay, so here's the kicker. If the universe is expanding, what happens if you run the movie backwards? Everything gets closer and closer and closer together until all the matter and energy in the entire cosmos is squished into one unimaginably hot and dense point. This was the logical and totally revolutionary conclusion.
But this idea of a beginning? Oh, it was not accepted overnight, not even close. In fact, it kicked off one of the biggest debates in the history of science, pitting two completely different views of the universe against each other.
The rival theory was called the steady-state model. Now, this was a clever attempt to accept that the universe was expanding while still hanging on to that comfortable old idea of an eternal cosmos. Its defenders basically said, sure, the universe is expanding, but it has no beginning and no end. To keep the density the same, they proposed that new matter was just continuously popping into existence out of nowhere, filling in the gaps as galaxies drifted apart.
This table really breaks it down perfectly. In the Big Bang corner, you've got a universe with a definite starting point. In the steady-state corner, it's eternal. For the Big Bang, the universe gets less dense over time. For steady-state, it stays the same. But the most important difference is that last one, evolution. One universe changes and gets older, while the other looks exactly the same, always. These are two profoundly different realities, and only one could be right.
And here is a fantastic little piece of history for you. The name Big Bang? It was actually made up by one of its biggest opponents, the astronomer Fred Hoyle. He said it on a BBC radio show to make fun of it, to make the idea of a cosmic beginning sound like some simplistic, absurd explosion. The name, of course, totally stuck. You can't make this stuff up.
So how do you settle a debate this massive? Well, you've got to find evidence. You have to search for a clue left over from the very beginning of time itself, some faint echo of creation.
I mean, that was the challenge, right? The steady-state theory said the universe has always looked the same, but the Big Bang theory said the early universe was totally different, that it was incredibly hot and dense. So if that was true, could there be any of that leftover heat still around?
And this is what makes a scientific theory so powerful. It doesn't just tell a good story. It makes a prediction you can actually go out and test. People like George Gamow realized that if the universe started in this primordial fireball, all that intense heat couldn't just disappear. It would have left behind a faint, uniform glow of radiation, an afterglow, that should still fill all of space, just cooled down to a few degrees above absolute zero.
And then, in 1965, two radio astronomers, Arno Penzias and Robert Wilson, found it completely by accident. They found this persistent, faint hiss of microwave radiation coming from every single direction in the sky. It was the cosmic microwave background, the echo of the Big Bang. This was the smoking gun. The steady-state theory had absolutely no way to explain it,
And just like that, the debate was pretty much over.
And the evidence just kept getting better and better. NASA launched the COBE satellite in 1989, and it made 2 discoveries that won a Nobel Prize. First, it confirmed that the energy signature of this radiation was a perfect match for what you'd expect from the cooling embers of the early universe. And second, it found these teeny tiny temperature differences, minuscule ripples that were the actual seeds from which all the galaxies we see today would eventually grow. Just amazing.
So, with the Big Bang on solid ground, scientists could finally start to piece together the universe's origin story with real confidence, starting from the very first crazy moments of existence.
The first second of the universe was, well, it was a frenzy of unimaginable change. As you look at this timeline, in the first sliver of a moment, the Planck epoch, all the forces of nature were one unified thing. Then, snap, gravity split off. That was followed by this insane burst of exponential expansion called inflation, which basically ironed out all the wrinkles in the cosmos. And finally, the strong nuclear force broke away, leaving behind a hot soup of fundamental particles.
And just look at those timestamps again. We're talking about numbers with dozens of zeros after the decimal point. The most important transformative events in the history of the universe happened in a time frame we can't even begin to wrap our heads around.
Now, fast forward about 380,000 years. The universe finally cooled down enough to be transparent. Protons and electrons got together to form the first atoms, and light was finally set free to travel across the cosmos. That freed light is what we now see as the cosmic microwave background. And what came next was a period of hundreds of millions of years called the Cosmic Dark Ages, just quiet darkness before the very first stars blinked on.
So, after figuring out the universe's incredible beginning, science naturally turned to the other great mystery. If we know how this whole story started, how's it going to end?
For decades, everybody just assumed the expansion of the universe must be slowing down, because, gravity. But in the late 1990s, astronomers found the exact opposite was happening. The expansion is speeding up. There's some mysterious anti-gravity force out there, which we now call dark energy, and it's pushing everything apart faster and faster.
This bizarre discovery leads to a few possible endings for the cosmos. You've got the Big Freeze, where expansion just goes on forever until the universe is a cold, dark, and empty wasteland. Then there's the Big Rip, a much more violent finale, where the accelerating expansion literally tears apart galaxies, stars, and even atoms. Or, if this dark energy thing gets weaker, maybe the Big Crunch, a total reversal of the Big Bang where gravity wins and pulls everything back into one final tiny point.
Based on everything we can measure today, from that echo of the Big Bang to the light from distant exploding stars, all the evidence is pointing overwhelmingly toward one particular fate. It really seems like the most likely end for our cosmos is a slow, quiet fade into the Big Freeze.
And that leaves us with a final, really profound thought, doesn't it? The grand story of our cosmos, which started in an unimaginably hot and violent fireball, seems destined to end in a cold, quiet, and eternal darkness. From a bang to a whimper. It's a humbling thought and a pretty incredible perspective on our place in this cosmic story.